Far away in a place where the sky is darker than memory, something ancient once burned with brilliance. It was a star massive, wild, alive with light and fusion. For millions of years it hummed its song into the universe, turning hydrogen into helium, light into warmth, silence into shine. But even stars have lifespans, and when their time ends, they do not vanish quietly. No, they go out in grandeur, collapsing into themselves with a final breath so heavy it bends space. What's left behind is not nothing. What's left is a heart, small, dense, and strange, a neutron star. A neutron star is not a ghost. It is not ash. It is not quite alive and not quite dead. It is what remains when all the light has been used up, when a star folds in on itself like a note crumpled tightly in a pocket of space. Imagine a teaspoon of something that weighs as much as a mountain. Imagine gravity so strong that atoms no longer hold their shape. The protons and electrons inside matter are crushed together, forming neutrons. And so this new thing is born, no longer a regular star but a neutron star, a core made of silence and pressure. These stellar remnants are small, only about 12 miles wide, yet they hold more mass than the sun. They don't shine like they used to. Their light is faint, a leftover whisper of their past, but they are heavy beyond belief, dense beyond imagination. If you stood on their surface, though no one ever could, gravity would pull you down with such force that even light would feel the weight. This is where matter ends and compression begins. This is where physics becomes poetry. Neutron stars spin, sometimes slowly, sometimes 1,000 times per second. They are like cosmic tops whirling in silence. Their spin is a memory of the star's collapse, all the energy once stretched wide now turned inward, tight and fast. These spinning stars are called pulsars when they beam out light like a lighthouse in the void. Every pulse is a rhythm, a beat, a celestial heartbeat echoing through the fabric of space. Even from 1,000 light years away, Earth can feel that pulse, tick, 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 like the breath of something ancient. Around them, space bends and curves. Time slows. Their presence makes a dent in the universe itself. They are so compact, so dense that they create ripples in gravity known as gravitational waves. When two neutron stars collide, a rare ballet of celestial bodies, the universe trembles. A faint quake of time and space shudders outward, carrying with it stories of gold, platinum, and other heavy elements formed in that stellar crash. It is believed that many of the metals we wear, the rings on our fingers, were born from the collision of two hearts that never died. If you were to get close to a neutron star, you would not see fire. You would not hear anything at all. But the feeling would be immense, as if the air had been pressed out of the universe, replaced with a pressure that comes from knowing you are near something that should not exist. They are so small, yet their mass is enormous. They are so quiet, yet they shape galaxies. Some scientists say they are like giant atomic nuclei, the densest matter outside a black hole. But in truth, they are more like secrets, the kinds too heavy to carry, yet too beautiful to forget. Their surfaces are not soft. The crust of a neutron star is harder than diamond, held together by nuclear forces that defy normal understanding. Beneath this crust is a sea of superfluid neutrons, particles that flow without resistance. Some say this inner ocean is colder than space itself, others that it behaves like a single quantum wave. It is the strangest matter we know, and still, we do not fully understand it. The magnetic fields of neutron stars are stronger than anything else in the cosmos, 1,000,000,000,000 times more powerful than Earth's. These fields twist and swirl, wrapping the space around them like invisible storms. In some neutron stars, these magnetic fields erupt, releasing bursts of radiation that travel light years. We call them magnetars, rare and wild, as if the universe still remembers how to shout. Yet for all their strength, neutron stars are fragile in another way. If they collect too much mass, they collapse again. Gravity wins and they fall inward, deeper still, becoming black holes, places where even light cannot escape. It is a quiet danger, a soft edge between being and vanishing. And so, neutron stars walk a line between presence and oblivion, between silence and echo. Scientists study them with radio telescopes, listening for their pulses like tuning into a cosmic lullaby. Each flicker, each tick of their spin, reveals clues about gravity, time, and matter. These distant hearts, compacted by fate, hold answers to questions we still struggle to form. They are mysteries pressed into spheres. If you close your eyes and imagine one floating in a cradle of darkness, spinning softly, you might feel the quiet thrum of it in your chest. Not a sound, but a presence. Not a light, but a memory. The universe, it seems, does not forget its stars. Even after their light has gone, their weight remains. Even after their stories have ended, their gravity speaks. And so the neutron star waits, tucked in the folds of the night, heavy with memory, dense with time. A place where the remains of a star become something entirely new, not gone, not glowing, but enduring, like the echo of a dream or the hush that follows thunder. This is the heart that didn't die. This is the star that folded inward, becoming smaller than anyone imagined and more powerful than anyone believed. Let's drift deeper now, into the quiet folds of matter and meaning, where neutron stars do more than sit in space. They teach us about the very limits of existence. If the first story of a neutron star is its formation, the second is how it continues, spinning in the afterglow of collapse, reshaping the rules of nature in its own hushed language. For within that tiny sphere, only 12 miles wide, the universe plays with the extremes of what can be. Here, density is no longer a measure. It becomes a sensation, an unrelenting pressure packed into a body so compact it could fit inside a city, yet so heavy it could pull at the bones of spacetime. And inside, the layers are nothing like those of Earth or even of normal stars. At the very surface lies a crust, rigid, crystalline, made from neutron-rich nuclei suspended in a sea of electrons. It is brittle but stronger than steel. Beneath that crust, atoms are squeezed so tightly that the distinction between them dissolves. It is here, in the inner regions, that nuclei lose their individuality, and matter becomes a fluid of neutrons, sliding past each other in perfect silence. A superfluid, something that flows forever without resistance, like time with no friction. This strange inner sea, they say, can spin at different speeds from the crust above, and sometimes, just sometimes, it catches. The crust lags behind, then slips suddenly, causing what we call a starquake. A neutron star flinches, and its rotation shifts, just by a tiny fraction, but enough for our instruments to feel the jolt from across the galaxy. It's like a shiver from something that forgot how to move but remembered how to tremble. These glitches, as scientists call them, are whispers of deep, internal change. A star trying to readjust, to settle once more into its impossible form. Even though these stars are so far away, we know them not by light alone but by their rhythm. The pulsars send out beams of radio waves in perfect timing, spinning like cosmic metronomes. Some tick every second, others faster than the blink of an eye. They do not vary. They do not stutter. Their signals are so precise, astronomers have used them to test the very shape of time itself. One, in particular, a pulsar in a tight orbit with another neutron star, allowed scientists to confirm Einstein's theory of general relativity with uncanny precision. As they twirled around each other, their orbits shrank ever so slightly, radiating away energy in the form of gravitational waves. It was as if these two dead stars were still dancing, giving off one last waltz, and in doing so, bending the universe ever so softly. The most magnetic neutron stars, the magnetars, offer a wilder kind of song. Their magnetic fields are violent, unstable, capable of twisting the crust with invisible force. When their fields snap and rearrange, they release bursts of energy so powerful they can affect satellites in Earth's orbit, even from thousands of light years away. These events are not explosions in the way we see supernovae, but flashes, sudden, intense moments of cosmic unrest. In 2004, one such flare reached Earth from across the galaxy and briefly outshone everything else in the sky. For a fraction of a second, our planet was bathed in the sigh of a magnetic star having a restless moment. Still, most neutron stars are quiet. They spin and shine with discipline, They are the clocks of the cosmos. Some have existed for millions of years, long after their supernova blast has faded from sight. And as they move through space, they gather whispers of the past, dust from other stars, cosmic rays. They do not forget. The information carried in their spin and radiation tells us about their birth, their journey, and the fabric of the space they cross. There is something profoundly emotional about their stillness. In a universe that is always expanding, always flying outward, neutron stars are the collapsed, the collected, the concentrated. They are what happens when everything is pulled inward and yet somehow still remains. They are grief solidified, the memory of fire turned into weight, a form of cosmic endurance, unyielding even after death. And in their dense interiors, something stranger still may wait. Some physicists believe that, under the most extreme pressures, even neutrons cannot remain as they are. They may dissolve into their constituent quarks, forming what is known as quark matter, a sea of up and down quarks, perhaps even strange quarks. This would make the neutron star a quark star, a kind of even more compressed object, where matter exists in a way we have never seen. It is only a theory, but one that invites wonder. Could the very core of a neutron star be not just dense, but a whole new phase of reality? As they drift through galaxies, neutron stars rarely interact. Their solitude is part of their story. Yet when two of them are bound by gravity, circling each other for eons, a collision becomes inevitable. And in that moment when they crash, the universe takes notice. The event gives off gravitational waves, ripples in spacetime that we now can detect. It releases gamma-ray bursts, the brightest explosions in the universe. And most mysteriously of all, it creates the heavy elements that make up so much of our world. Gold, platinum, uranium, these are not formed in normal stars. They are born from neutron star collisions, scattered into the universe by those final, violent unions. What you wear on your wrist, what glints in wedding bands and old treasure chests, these are the echoes of dead stars meeting one last time. The poetry of it is undeniable. From the death of light comes the birth of value. So we study them, not only to understand stars, but to understand matter. Neutron stars press on the boundaries of our knowledge. They force us to think about what happens when matter is pushed to its final state. They show us gravity not as a pull, but as a force that can hold time itself. They reveal how something so small can carry weight not just in mass, but in meaning. In every way they are contradictions, incredibly small yet unimaginably heavy, invisible yet measurable, dead yet still moving. And their presence reminds us of a truth often forgotten, that even endings can be rich with rhythm. That even the most violent transformations can give rise to order. And that somewhere in the folds of night, something collapsed, and from that collapse, a new kind of beauty was born. When we listen to the pulse of a neutron star, we are not just hearing a star. We are hearing the universe trying to remember what it once was, a whisper of light now turned into gravity's breath. You can almost feel it, can't you? That quiet hum of something spinning in the dark, not gone, not loud, but very, very real. Now imagine drifting even deeper into that cosmic hush, where the light no longer flickers and the sounds of the universe have turned inward. In this stillness, the neutron star remains, steady, humming, breathing with gravity's slow rhythm. It does not demand to be seen, nor does it wish to be touched. It simply is, like a thought the universe cannot forget. This is where we find the quiet wisdom of what remains after fire, after light, after the storm of collapse. Neutron stars are not only objects of study, they are reminders. They are what is left when a star has given everything it can. Think of a star not as a light in the sky, but as a process. For billions of years, it fuses elements, radiates energy, and shapes the cosmos with its warmth. But when the core runs out of fuel, gravity presses inward, unstoppable and patient. Most stars become white dwarfs. Some vanish into black holes. But the ones in between, the ones that teeter at the edge of destruction and still resist, those become neutron stars. Their resistance is not defiance. It is inevitability wrapped in patience, mass wrapped in silence. Their very form says, I have collapsed, but I have not vanished. They are made of neutrons, yes, but also of pressure, unimaginable pressure. It is this pressure that holds them together, that keeps them from becoming black holes. The same gravity that crushed their core is now what keeps them intact. Every bit of them is compacted into a balance between falling and standing still. This tension between collapsing further and holding on defines their existence, and it gives them a kind of grace, a posture of quiet endurance. Astronomers peer into the skies with giant dishes and precise instruments, scanning the heavens for regular beats. When they find them, they know this is no accident, this is no random flicker. This is the call of a neutron star. Some pulses have been ticking for millions of years, unwavering, precise to the fraction of a second. Even atomic clocks here on Earth must bow to their steadiness. In a universe filled with chaos, here is order. In the debris of a once violent death, here is rhythm. Somewhere spinning through a silent galaxy, a pulsar keeps time for no one. Its beams sweep the dark, rotating with such discipline that a single tick missed would shake the certainty of the cosmos. That is the trust we place in these stars, not only to exist but to mark the passing of time itself. And they do. With every rotation they log the age of the universe. They tell the story of when they were born, how fast they spin, how the space around them bends. They are timekeepers wrapped in steel, astronomers of gravity itself. And still, for all their scientific clarity, there is something deeply human in our fascination with them. Perhaps it is because they remind us that even in endings there is something that holds, something that survives. We like to think that collapse means loss, that when something burns out it is gone. But neutron stars teach a different lesson, that what is left behind can be powerful, even beautiful. That even after light has vanished, there can be pulse, structure, meaning. Neutron stars also stretch our imagination. We cannot truly fathom what it is like on their surface. If you stood there, a thought experiment only, you would be crushed instantly by gravity 10 billion times stronger than Earth's. The crust beneath your feet would be solid iron, dense beyond reason. Above you, the magnetic field would swirl invisibly, capable of tearing atoms apart. And yet, in that unimaginable setting, there would be quiet. No atmosphere, no weather. Just the soft spin of a star that once roared and now whispers. Their interiors are even stranger. Superfluid matter, quarks perhaps. Some theories speak of exotic particles like kaons or pions swimming in that dense sea. These are not everyday ideas. These are glimpses into the edge of what physics allows. Neutron stars are laboratories we cannot visit, but whose results arrive with every radio wave. Every beam tells us something about the forces that bind the universe: strong force, gravity, magnetism, not in theory but in action. And then there are their collisions. Two neutron stars spiraling into each other, locked in a gravitational embrace for eons. When they finally meet, the collision sends out a tremor through the very fabric of spacetime. We call it a gravitational wave. We've only just begun to detect these. LIGO, the great listening ear of our planet, picks them up like the rustle of distant thunder, and when it hears one, we learn. We learn about matter, energy, and the alchemy that forms the elements of our Earth. In August 2017, we witnessed such an event. Telescopes across the world watched the sky brighten. Instruments across the spectrum recorded the afterglow. And in the faint gold that followed, we found our origin story, the birth of heavy elements, of gold and platinum, scattered like stardust across the galaxy. That wedding ring on your finger, it may have come from the final sigh of two neutron stars colliding in the dark. A love story of gravity and collapse, etched into the atoms of Earth. Now rest with that image for a moment. A collapsed star spinning in the night, a pulse that does not fade, a storm of magnetic fields and gravity bound into a sphere no wider than a city. This is not science fiction. This is the real universe, and in its stillness there is beauty, a quiet that says, "We were once fire and now we are time." A silence that sings louder than light. The neutron star does not move fast through space, but it turns, and in that turning it endures. So the next time you look at the stars, remember this. Somewhere among them is one that collapsed but did not die. One that shines with a memory instead of light. It may be sending out a pulse right now, ticking across the cosmos. And even if you cannot see it, it is there, small, heavy, constant. A reminder that even when things fall inward, something meaningful can remain. In the end, the neutron star is not a grave. It is not a tomb. It is a continuation, a different way to be. It is the universe's way of saying, I remember. And perhaps that is what we all wish for, to become, in some form, a memory that never fades. In the deepest stretches of the sky, where no wind stirs and time slows to a quiet hum, something unseen is always working. Not a force we can touch, or a presence we can hear, but something that cradles every planet, every moon, every star. Gravity. Gentle and patient, it binds the cosmos with arms we cannot see. And when a star dies, collapsing inward with all the weight of its own brilliance, gravity is the one that catches what remains. In that soft net of spacetime, the star becomes a memory, folded tightly into something smaller, stranger, and infinitely dense. A neutron star, the ghost of what once burned. We often imagine gravity as a pull, a downward tug that holds our feet to the earth. But in the quiet mathematics of the universe, gravity is not a rope or a magnet. It is the shape of space itself. It curves. It bends. Where mass exists, space folds. The heavier the mass, the deeper the curve. And when that mass is compacted, like the remains of a collapsed star, the curve becomes steep, a well in the fabric of the cosmos. This is gravity's secret. It does not reach out, it simply shapes what is already there. And all things follow that shape, moving not because they are pulled, but because they are falling into curved paths. Imagine a ball resting on a stretched blanket. Place a heavy stone in the center and the ball rolls toward the dip. Not because it is being drawn, but because the surface beneath it has changed. So it is with space. So it is with gravity. A neutron star, small as a city but heavy as a sun, presses deep into spacetime. Around it, space swirls and time stretches. Clocks tick slower near its surface. Light bends. Nothing is quite as it was. This is the star's ghost, not invisible but invisible by design. Neutron stars do not glow like their living parents. Their light is not soft and golden but cold and sharp, often only visible in radio waves, X-rays, or gamma rays. Yet their presence is felt in the way other stars orbit them, the way gas swirls in spirals before falling in. Even when silent, their gravity speaks. And what it says is this: I am still here. I still hold weight. I still shape the universe around me. When a massive star explodes in a supernova, its outer layers are thrown outward in a grand, glittering burst. But the core, having spent its fuel, collapses under its own weight. This implosion is not chaos. It is precision. Protons and electrons fuse into neutrons, space tightens. And in that collapse, a neutron star is born, dense, compact, and curled tightly into gravity's embrace. It is no longer a furnace of fusion. It is something new, something folded. The cradle that holds it, gravity, does not let go. It wraps around the neutron star like silk pressed into stone. And in this embrace, new things happen. Light cannot escape easily. Time crawls. Even nearby particles are crushed or flung away. The star is held in place not by walls but by curves. Its mass makes space around it bow inward, as if the universe itself is kneeling at the memory of what was lost. If two neutron stars circle each other, gravity keeps them dancing for millions of years. They spiral slowly inward, step by step, releasing tiny ripples in the fabric of spacetime, gravitational waves. These waves travel outward at the speed of light, carrying the echo of the star's motion across galaxies. When finally the two remnants collide, their union is fierce and bright. Gold is forged. Space is wrinkled. The cradle that once held each alone now tries to hold them both, and sometimes it cannot. If the new mass is too great, gravity gives in and a black hole is born. The star's ghost, once visible in radiation and spin, vanishes into the darkest fold of space. But until that moment, gravity holds. It does not rush. It does not tear. It waits. Its strength is in patience, in the way it bends reality without noise or warning. Even neutron stars that travel alone, hurtling through space at incredible speeds, are held by gravity's net. They cannot escape the galaxy, no matter how fast they go. The arms of the Milky Way curve gently inward, guiding them always back toward the heart. Gravity is not only the shape of space, it is also the rhythm of time. Near a neutron star, time slows. A second on its surface may be longer than a second far away. This difference is not noticeable in everyday life, but in the realm of collapsed stars it is profound. It means that every neutron star is not just heavy in space, but heavy in time. Its presence presses down on the ticking of the clock, making time drip instead of flow. And in this slow drip, the universe keeps count. Some neutron stars are born with companions, other stars that orbit close by. These companions may lose matter to the neutron star, pulled by its gravity into thin, spiraling disks of hot gas. As the matter falls in, it heats up, emitting X-rays that we can see from Earth. These are X-ray binaries, couples in which one partner is invisible but unmistakable. The neutron star, dark and dense, feeds slowly on its companion's light, not with hunger but with inevitability. Gravity is not greedy, but it accepts what falls. Even as we speak, neutron stars are moving. They are not frozen in the sky. They travel through galaxies, remnants of ancient explosions. Some move at speeds of hundreds of kilometers per second, flung outward by the violence of their birth. But wherever they go, gravity follows. It shapes their paths. It defines their destinations. Like marbles rolling across a vast, curved surface, they follow lines laid out by mass and distance, by the invisible curves that stretch across the void. To imagine all this, to hold it in the mind, is to feel small, and yet deeply connected. For gravity that binds a neutron star is the same that holds you to the Earth, the same that guides the moon in its orbit, that shapes the rise and fall of tides. It is universal. It does not choose. It does not end. The gravity that cradles a collapsed star is the same gravity that caught you when you took your first step. In this way, neutron stars are not just curiosities. They are reminders that even in the wake of explosion there is order. Even after collapse there is structure. And behind it all there is gravity, silent, unseen, but always present. It does not shine. It does not shout, but it holds. And in its hold, the ghost of a star becomes something real once again. Let's fall gently now into the deeper layers of this mystery, where gravity does not just hold, it sculpts. In the belly of a neutron star, where time is thick and matter is strange, gravity acts not like a force but like a memory pressed into the bones of the universe. Every part of the star is shaped by it, wrapped in it, defined by its insistence. The crust, brittle and strong, is stretched tight over oceans of particles that cannot be seen, only felt. Beneath the crust, the neutrons form rivers that never stop flowing. They move without friction, without heat, without pause, superfluids, cooled to near absolute stillness, but never quite asleep. They swirl in silence, as if remembering the motion of the star that came before. Inside this cradle of gravity, the rules of matter bend. Atoms no longer keep their familiar shape. Protons vanish into the press of pressure, and electrons are swallowed by their opposite. Only neutrons remain, each one nudging against the other, packed so tightly that the space between them disappears. The whole interior becomes a single thing, not a mixture of particles, but a collective whisper of collapsed light and fallen structure. This is not how matter behaves on Earth. This is how it behaves when it remembers what it used to be, and what it was before that. And yet, even here, structure persists. Scientists believe that the layers of a neutron star follow a strange order: outer crust, outer core, inner core. Each layer is denser than the one before, each boundary a quiet agreement between forces almost too powerful to name. In the outer crust, iron nuclei drift in a sea of electrons. Deeper down, these nuclei stretch and deform, becoming spaghetti-like strands, lasagna sheets, or other forms scientists poetically call nuclear pasta. These names are soft compared to the reality they describe, the densest forms of organized matter known, shaped not by taste or touch, but by the will of gravity and the crush of collapse. The outer core may contain superfluid neutrons and superconducting protons, matter that behaves like music, flowing without resistance and humming with electromagnetic patterns. And deeper still, in the inner core, the theories become even wilder. Perhaps there is quark matter, a state where neutrons dissolve and their building blocks roam free. Or maybe hyperons appear, particles made from strange quarks, behaving in ways no one has ever seen. These possibilities exist not in laboratories but in equations and models. We cannot reach them, but we know they are real because neutron stars speak through their gravity. When two of them collide, the result tells us what they held. In 2017, when the light and gravitational waves from such a collision reached Earth, we saw not only the brightness of the explosion, but the fingerprints of the elements created. The spectrum of light revealed gold, platinum, and other heavy atoms, formed in the flash of fusion and flung into space like dust from a cracked mirror. We watched it, measured it, and realized, this is how the rarest parts of Earth were born. In a cradle of gravity, in the joining of two ghosts. These waves, these ripples, are gravity's voice. Until recently, we only heard gravity through its consequences, orbits, falls, tides. But now we can listen. LIGO and Virgo, great detectors built to feel the tremble of spacetime, have opened our ears to a new kind of astronomy. We no longer just see the stars, we feel their weight. And when we feel that weight change, when a neutron star collapses into a black hole or collides with its twin, we know it through the trembling of spacetime itself. Like hearing the sigh of a mountain from across an ocean. The elegance of it is quiet. The pulse of a neutron star, the orbit of a binary pair, the crash and release of gravitational waves, all of it unfolds in rhythm. Gravity does not shout. It insists. It sculpts. It waits. And in doing so, it turns even a collapsed star into something with structure, purpose, and persistence. Even alone, a neutron star is never unmoored. It orbits the galactic center like a candle in the wind, moved by the curves of the Milky Way's own gravity. In its motion, it carries the shape of the galaxy, the pattern of its place. It is part of something larger always. Its gravity tugs gently at passing dust, stirs invisible ripples in interstellar gas. And if another star wanders too close, the neutron star may steal from it, not with malice but with inevitability. Its cradle is deep, and what falls into it rarely climbs out. In some systems, a neutron star becomes a beacon. Matter from a nearby companion spirals in, forming an accretion disk that glows brightly in X-rays. The gravity of the neutron star heats this matter to millions of degrees, lighting the sky with energy that we can see from halfway across the galaxy. These are not ordinary stars. These are X-ray binaries, glowing warnings of the presence of a deep, invisible well, a cradle-turned furnace. And yet with all their density and power, neutron stars are also fragile. Add too much mass and they collapse further. Gravity's cradle, once tight and steady, gives way. The star becomes a black hole, vanishing not in light but in curve. The ghost becomes a shadow, and though the process may be silent, the change is profound. The cradle of space folds inward so sharply that even time no longer escapes. It is not death, it is transformation, but a transformation from which no story returns. This is the threshold neutron stars walk. They are balance. They are tension held still, not quite alive, not quite gone. Their gravity holds them just this side of silence, and in that balance they offer a kind of grace, the stillness after collapse, the hush after a storm. The sense that even in the universe's most violent acts there is aftermath, and in that aftermath there is shape. We measure them, we chart their paths, we model their layers, but always we return to wonder. How can something so small hold so much? How can a cradle of gravity be so firm, so deep, and yet so quiet? How can time itself slow down near these stars, as if pausing to honor what they've become? Perhaps because gravity in the end is the oldest story. Long before light, long before atoms, gravity was already shaping, already bending, already cradling what would someday become stars. And now in the hushed bodies of neutron stars we see its gentlest work. Not the chaos of birth or the flare of death, but the persistence of what remains. The soft hands of spacetime holding what once burned, whispering, "You are not gone. You are folded. You are part of the shape of everything." And now we arrive at the quietest place in this journey, the moment after understanding when all that remains is presence. The neutron star no longer asks to be discovered, no longer pulses its name in waves of light. It simply exists, folded into the gentle hold of gravity, wrapped in a stillness so complete that it becomes a kind of wisdom. There is nothing hurried here, no drama, only the memory of a star that once burned and the shape of space still cupped around its core. This is gravity's secret cradle, not a prison, not a trap, but a lullaby written in the language of curves. In this final section, let us not rush. Let us imagine the world from the perspective of a neutron star, not as an object, but as a way of being. All around, the universe expands. Galaxies spin, stars are born, comets arc and vanish. But here inside the cradle, everything is still, not frozen but settled. Gravity does not demand attention. It does not twist or scream. It leans, it shapes, it waits. And in doing so, it becomes the foundation upon which silence can rest. The neutron star is alone but not lonely. It is part of the galaxy's memory, moving through invisible pathways carved long before it was born. Its journey is quiet, its motion slow, but its presence undeniable. Even after eons, it carries mass, the kind that bends time, shifts light, holds fast against the pull of disappearance. It does not need to shine. Its weight is its story. Its silence is its song. Some neutron stars spin still, their pulses regular, like the ticking of a forgotten clock in a forest no one walks. Others have slowed to near stillness, their light faint, their field soft. These ancient ones are called dead pulsars, but even death is too loud a word. They are simply resting, still turning, still held, still curving space around them. Their energy has dimmed, but their gravity remains. And that gravity, even now, shapes the stars that pass too close, guides the dust that drifts nearby, joins the slow ballet of the galactic disk. There is something deeply moving about this kind of endurance. The way a neutron star continues to exist, even after the fire is gone, even after the spin has slowed. It is not trying to be anything else. It does not resist its nature. It simply becomes what the universe made it into, a remnant, yes, but also a reminder that what we are is not just what we burn with, but what remains when the fire is done. Think now of the fabric of space itself. Think of how it wraps around this tiny, heavy thing, as if remembering the larger star it once held. The curves do not vanish when the light goes out. The crater in spacetime stays. It is gentler now, perhaps, but no less deep. A kind of gravitational scar, pressed softly into the shape of forever. That's what gravity leaves behind, not flames, but fingerprints. And still it gives. It allows others to learn. Through neutron stars, we test our greatest theories. We measure the weight of space, the stretch of time, the speed of gravity's whisper. We ask impossible questions. What happens to matter at the edge of collapse? How does light behave near the densest known objects? Can time stop, even briefly, in the arms of a collapsed star? And the answers come, not in language, but in pulses, in curves, in silence. The soft precision of these answers humbles us. We build instruments that stretch across mountains just to listen. We send satellites into the dark just to catch a flash. And when we do, it is always fleeting, a burst, a tick, a tremor. But from that small moment, we learn something enormous, that gravity is not just a force. It is a storyteller, a gentle one, a slow one, but one whose stories shape galaxies. And if we look inward, we find that gravity lives here too. It binds us to the earth. It pulls the moon in rhythm with the tides. It holds our bodies together from skin to cell. Without gravity, our blood would drift, our bones would soften, our breath would float away. We live because of this invisible companion. And so, when we study neutron stars, we are not looking out into something foreign. We are looking at an echo of what holds us every day. The same cradle, just deeper. Imagine the universe as a garden, vast and blooming. Neutron stars are the seeds that remain after the blossoms fall, compressed, dark, small, but filled with potential, with memory. They remind us that beauty doesn't always shine. Sometimes it rests, sometimes it waits, and sometimes it simply is, sitting in the dark, heavy with meaning. And what of the future? What happens when even these stars grow cold? When their pulses cease entirely? Will the universe forget them? No, because gravity forgets nothing. The curves in spacetime remain. The orbits shaped by their presence continue. The elements they gave birth to, gold, platinum, heavy iron, will circle in planets, live in blood, glint in rings and tools and timepieces. We wear their legacy. We live within their story. So the cradle does not close, it holds. Even when light is gone, even when motion fades. The neutron star remains part of the map, part of the music. A soft chord in the background of the cosmos, so deep and low it's easy to miss. But once heard, it stays. It is not dramatic. It does not change shape. But it is always there, the quiet presence of what survived. Close your eyes for a moment and imagine a place where space curves inward like a cupped hand. A place where time slows, where matter sleeps in impossible states, where silence is thicker than stone. That is the heart of a neutron star. That is the cradle gravity builds. And in that cradle the universe tucks away the memory of brilliance, the core of light turned inward. Not forgotten, not gone, just changed. Let that be enough. Let it remind you that even the most explosive endings can leave something enduring. That even in the darkest corners of space, the shape of a vanished star can still bend the present, and that the soft hand of gravity, invisible and endless, is always holding, always cradling, what came before. When a star dies, it does not slip quietly into the night. It explodes, spilling its insides into space in a brilliant, final act of brightness. This is the supernova, a blaze so fierce it outshines entire galaxies, a heartbeat so loud it echoes for centuries. But what comes after? After the light fades and the fire dims, what remains in that silence? What lingers in the cold wake of such cosmic drama? This is the story of what follows: the brightest farewell, the gentle debris, the wandering whispers, the stardust that falls slowly through the arms of galaxies. This is the silence after light. A supernova begins in the quiet core of a massive star. For millions of years, the star has burned steadily, fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen. This is how stars live, by creating, but the process cannot go on forever. Eventually, the star builds up a core of iron, and iron cannot burn. It does not release energy, it absorbs it. And so, the star reaches a limit. The outward push of fusion weakens. The inward pull of gravity grows stronger, and in a single moment, balance breaks. The core collapses inward at incredible speed, crushing matter into a state beyond understanding. Then almost instantly it rebounds, a shockwave ripping outward through the star's layers. The result is the supernova, a vast eruption of energy, light, and particles. It can last for weeks in our skies, glowing like a new sun where none was before. But even this brilliance fades. And once it does, a strange quiet takes hold. What remains is not emptiness. It is not nothing. It is a cradle of change, the first breath of a new kind of existence. The star's outer layers scatter into space, forming nebulae, great clouds of gas and dust that drift for centuries, illuminated by the dying glow of radioactive decay. These remnants are beautiful. They paint the sky with soft colors, blues, greens, deep purples. They swirl in slow motion, like thoughts drifting in water. We see them through telescopes as fogs of memory, the handwriting of a vanished star still hanging in the air. And in the center of this quiet storm, something heavy remains. If the star was large enough, it may leave behind a neutron star or perhaps a black hole. If it was smaller, it may vanish entirely, its gases thinned into the interstellar medium. But always something lingers. The silence that follows a supernova is never empty. It is filled with echoes, particles, radiation, movement, memory. These particles, protons, neutrons, neutrinos, scatter through the galaxy. Some race away at near the speed of light. Others linger, caught in the magnetic nets of stars. Some find their way into new clouds of gas, helping to form new stars, new planets, and eventually new life. The iron in your blood, the calcium in your bones, the gold in your ring, these came from supernovae. They are pieces of stars that died long before Earth was born. You carry the silence after light in your body always. Even the radiation continues. For thousands of years, the remnants of a supernova emit energy, X-rays, gamma rays, radio waves. This energy travels outward, cooling, spreading, becoming part of the quiet noise of the universe. Astronomers detect it still, centuries after the explosion. In some parts of the sky, they find rings of shockwaves still expanding. In others, they find spinning neutron stars, pulsars, ticking out the last rhythm of a once mighty heart. These pulsars are strange. They are small, dense, and quick, rotating many times per second, sweeping beams of energy through space like cosmic lighthouses. Each pulse is a reminder: the star is gone but not erased. Its core remains, held tightly by gravity, compressed into a ball of neutrons barely the size of a city. The light is gone, but the motion endures. The silence is not absence, it is transformation. And the nebulae grow, they drift, they cool. Over tens of thousands of years, they may mix with other clouds, forming new stellar nurseries. There, the materials of the old star, carbon, nitrogen, oxygen, become the seeds for new stars. And so, the cycle continues. The death of one star gives rise to the birth of many. The silence after light is not the end of the story. It is the pause between verses in the song of the cosmos. In that pause there is wonder. There is space for reflection. The light dazzles, but the silence carries the truth that nothing in the universe ever truly ends. It only changes form. The star becomes a cloud. The cloud becomes a star. The light fades, but the atoms remain. They float, drift, gather, ignite, over and over endlessly. Even from Earth, we can see the aftermath. The Crab Nebula, born from a supernova witnessed in 1054, still glows in our telescopes. Its core, a pulsar, still ticks. Its tendrils of gas still spread. And though nearly 1,000 years have passed since its light first touched human eyes, its story continues. That is the power of the silence after light. It endures. And in that endurance, we find something human. We too shine and fade. We too leave behind remnants not of gas and plasma, but of love, memory, presence. And just like a supernova, the brightness of our lives gives way to a quieter legacy, a kind of gravity that holds even after we are gone. So the next time you look at the night sky and find a space where light used to be, know this: the silence you feel is not emptiness. It is history. It is future. It is the universe remembering what once was and quietly preparing for what will be next. Let us drift now into the deepening calm that follows the burst. The supernova has released its roar and the blaze has retreated back into stillness. But within that stillness, the universe begins its quiet rearrangement. It does not hurry. The remains of the star, scattered and spinning, begin to settle into new roles, no longer the burning core of a sun, but something softer, stranger, something in between being and becoming. This is the unfolding of the silence after light, not as an absence, but as a transformation, a new structure built from what once danced in fire. The cloud of gas and dust left behind the nebula is not just drifting aimlessly. It is a living map of energy, temperature, and memory. Within it, strands of magnetic field lines twist and turn, guiding particles through intricate patterns. Radiation seeps out gently, softening into radio waves and gentle pulses that move outward like echoes in an endless canyon. The light is no longer visible to our eyes, but it still travels. And where it touches, it tells the story of a star that ended in brilliance and then chose quiet. At the center, the neutron star may remain, a relic of collapse, dense and unbroken. Its surface, smooth and solid, holds matter packed so tightly it defies comprehension. Its gravity continues to shape the space around it, and if it spins, it sings. This song is not one of music, but of rhythm, a ticking, pulsing beat of electromagnetic waves. These pulses, when caught by telescopes, become the fingerprints of a vanished light. The neutron star does not glow with fire, but with memory. It is the keeper of a silent legacy. Around this core, the gas continues to spread. Photons race ahead, carrying energy to the edges of the nebula, pushing the frontiers of the explosion outward. This expansion is slow and graceful. Over time, the cloud may stretch across light years, a veil of thin color embroidered with traces of iron, silicon, calcium, and oxygen. Each element tells a part of the star's final tale: what it burned, how it ended, what it gave back to the cosmos. These clouds, fragile and faint, are where future stars may someday form. The silence after light is not a blank space. It is textured, layered, rich with movement too slow to see. Shockwaves ripple through interstellar space, heating nearby gas and stirring the dust. In some places, new shapes form, knots, filaments, waves. These are the first threads of cosmic rebirth, spun from the remnants of collapse. They do not glow, not right away, but they are building towards something. The silence is already stitching together the next chapter. In the stillness, neutrinos pass, ghostly particles created in the heart of the explosion. They move through the universe almost untouched, slipping through stars, planets, and even you without pause. These particles carry with them the direct evidence of nuclear reactions that shook the star apart. Their silence is not weakness. It is subtlety. A message whispered so quietly it requires deep listening to hear. And we have learned to listen. Instruments buried deep underground wait patiently for the faint signature of a passing neutrino. And when it comes, we know a star has spoken, not with brightness, but with breath. Sometimes, what remains of the supernova becomes more than a nebula. It can become a nursery. If the surrounding gas is dense enough, gravity may begin its slow, careful work again, pulling together the drifting materials. Dust gathers, hydrogen collects, temperatures rise, and over millions of years, a new star may ignite not as a replacement for the old, but as its heir. The silence after light has become the breath before light again. This is the cycle the universe honors. Not creation, then destruction, but creation, then transformation. Even when no new star is born, the materials enrich the galaxy. The interstellar medium becomes seeded with heavy elements. Future worlds may form with this material, planets with iron cores, atmospheres with oxygen, water that carries traces of ancient calcium and carbon. The elements of life are not original. They are inherited. They come from stars that lived long ago, died brilliantly, and then whispered their atoms across space. We are the children of those whispers. The silence after light is in our bones. Astronomers often speak of light echoes, a phenomenon where light from a supernova reflects off distant dust clouds, arriving at Earth long after the original explosion. These echoes allow us to see the past unfold in slow motion. Imagine that, a single supernova sending out ripples of brightness that bounce through space for centuries. Each reflection a delayed memory, a light that returns to us like a dream retold. This is how generous the universe is. It does not let its stories vanish. It lets them linger, reflect, return. In the modern sky, we see remnants of many such explosions. The Veil Nebula, the Crab Nebula, the remnants in Cassiopeia and Cygnus. Each one is a painting left behind by a star that ended long ago. And yet the picture is still changing. Gas still moves. Light still travels. The silence after light is not frozen. It breathes, expands, softens. It becomes background music to the universe's unfolding. From Earth, we often look up and marvel at the stars' brightness. But the spaces in between, the dark regions and the soft halos, are just as alive. They are filled with what remains after the flash. And in that remaining there is purpose. Gravity continues its quiet work. Electromagnetic fields hum. Radiation whispers. All of it creating the conditions for what comes next. We tend to think of silence as a kind of nothing. But in the language of the universe, silence is often the richest chapter. It is where light's loudness settles into meaning, where the rush becomes reflection, where the storm's edge becomes the seedbed for calm. So here in the long afterglow of a supernova is not loss but legacy, a beauty born not of brightness but of quiet continuation. The star gave everything, and the universe accepted it, scattered it, softened it, and began to build again. The silence after light is not the end. It is the deep breath the cosmos takes before whispering life once more. Let us walk now into the final echo, where light has long faded and only memory remains. In this silence after light, there is a softness that cannot be measured, a quiet that wraps itself around every leftover atom, every drifting particle, every story that still floats through the galaxy. This is the lingering, the aftermath, the hush that follows the song of collapse. The star is gone, its brilliance dissolved into dust and wave, but what it has left behind hums with quiet meaning. For even in absence there is form, even in stillness there is gravity, even in the end there is something that holds. Over time, the supernova remnant continues to stretch, curling into spirals and threads that wind through the interstellar medium. These tendrils, almost transparent, move gently, like the arms of a dancer long after the music has stopped. They carry traces of all that came before: helium from the earliest fires, oxygen and carbon from the late stages of fusion, iron from the final breath. These are not just elements. They are the alphabet of future life, waiting to be read again by newborn stars. And amid this drifting, sometimes something unexpected happens. A neutron star, once spinning fast, bright with pulses, begins to slow. The magnetism that defined it softens. The rhythm that once echoed through space becomes a whisper, then a pause. These silent pulsars are not gone. They are simply resting deeper within gravity's fold. Their spin slows to a crawl, their light dims beyond detection, but their weight, their presence, remains. They become unseen sculptures of density, shaping space with their mass alone. Elsewhere in the galaxy, the stardust scattered by their parent supernova is already mixing with other clouds. In dense pockets, gravity pulls the debris together. Atoms find atoms, molecules begin to form, and in time stars spark into being, young, golden, fresh with the heat of fusion. Around them, disks of dust swirl and condense. Planets begin to coalesce, rocky worlds, icy moons, gas giants cloaked in storms. These planets, unknowingly, are built from the bones of ancient stars. Their soils hold the fingerprints of supernovae. Their skies shimmer with light that once passed through fields of gas forged in collapse. And if one of those planets is just the right distance from its sun, if it has liquid water, a stable surface, an atmosphere gentle enough to cradle chemistry, then life may rise. Slowly, quietly, across billions of years, cells may form, multiply, adapt. And in the minerals of those cells, in the iron that carries oxygen, the calcium that builds bones, the carbon that binds it all, are the remnants of that long-dead star. The silence after light does not just linger. It becomes breath. It becomes heartbeat. Back in the darkness, the nebula continues to fade. Over tens of thousands of years, the once vivid cloud grows thin. Its filaments stretch farther. Its edges dissolve. Eventually, it becomes indistinct from the interstellar medium, no longer a glowing sculpture but part of the galactic fabric. Yet still, we remember. Still, we can see it through our instruments in long exposures and deep field surveys. Still, we chart its dimensions, measure its chemicals, trace its motion. Because even when the light is gone, the story is not. And stories matter. We are in many ways made of them, not only of atoms but of meaning. And the silence after a supernova tells a story of immense transformation, from fusion to collapse, from explosion to expansion, from light to dust to life. It is a story of how endings become beginnings, how death gives shape to birth, how silence carries the seeds of the next voice. The universe is full of such silences. Between the stars, between the pulses of neutron stars, between the ripples of gravitational waves. But these are not voids. They are waiting spaces, fields of potential, stillness before the next unfolding. When a supernova ends, it does not erase what came before. It amplifies it, spreads it outward, makes it available to more places, more futures, more dreams. Even black holes, those ultimate endpoints, are born from supernovae. If the collapsing core is heavy enough, gravity takes over completely. The star folds inward, not just into density but into invisibility. And yet the black hole is not absence either. It affects everything around it. Stars orbit it. Gas spirals into it. Time curves sharply near its edge. And still, the galaxy carries on, adjusted, reshaped, but undisturbed in its rhythm. The silence after light is also a lesson. That brilliance is not the only way to be. That quietness has power. That the unseen can still be felt. The universe does not insist on constant spectacle. Much of what it does is subtle, slow flows, gentle shifts, atoms drifting across billions of years to become part of something meaningful. The loudness of the supernova is not its legacy. Its legacy is in the things it touched long after the light faded. You can imagine it now, can't you? Somewhere in space, a dark, empty-seeming patch. No glowing star, no vivid color. But inside that patch, a neutron star ticks quietly, or perhaps no longer ticks at all, just exists, pulling on the fabric of space with the weight of what it used to be. Around it, a fatting nebula gossamer thin, trailing light through the dark. And far away, a young star just beginning to form, drawing from the dust of that explosion. And even farther, a planet, warm and blue, where someone someday might look up and wonder. And perhaps they'll find the clues, the radiation still echoing, the light bouncing from dust, the elements etched into stone. And they'll know something powerful once passed this way. A star ended, but not all at once, not completely. Its silence lasted longer than its sound. Its dust lived on in other skies. Its meaning folded itself into the next. And that is how the cosmos carries on, not in noise, but in memory. Not in fire alone, but in the hush that follows. A silence thick with everything that came before and everything still to come. In the deep hush of the cosmos, far beyond the warmth of our sun and the swirl of familiar stars, there are clocks that do not tick but spin. They do not chime but pulse. These are the pulsars, the lighthouses of the galaxy, stars that once blazed with fusion, then collapsed into silence, only to rise again as rhythm. They do not shine steadily. Instead, they flash precisely, again and again, like the universe breathing in a metronome's calm. And through these pulses, we come to know time not as a number but as a feeling, regular, measured, eternal. Pulsars begin their lives in chaos. Born in the final seconds of a supernova, they are the dense cores left behind when a massive star collapses. The explosion is vast, but the heart that remains is small, about 12 miles wide and unimaginably heavy. The matter inside is crushed to its limit, atoms broken down into neutrons, the star becoming a neutron star. But if the original star was spinning before its death, even slowly, the collapse speeds up that rotation. Like a figure skater pulling in their arms, the smaller the body becomes, the faster it spins. And so, from the wreckage, a pulsar is born, rotating hundreds of times per second, silently slicing through space. These stars do not pulse because they flicker. They pulse because of their shape. A pulsar has strong magnetic fields that beam light from its magnetic poles, but those poles are not aligned with its spin. So as the star rotates, its beams sweep across space like the spotlight of a distant lighthouse. If Earth happens to lie in the path of one of those beams, we see a flash, then another, like a cosmic heartbeat. To us, it feels like a pulse. But in truth, it is the spin of a silent body, curved by gravity, outlined by radiation, and dancing in perfect rhythm. And this rhythm is not random. It is precise beyond anything we experience on Earth. Some pulsars tick faster than atomic clocks, the most reliable timepieces we know, and we use them as such. We mark years with them. We test physics with them. We measure gravitational waves by watching how their rhythm shifts ever so slightly as the fabric of space stretches or compresses. Pulsars are more than stars. They are instruments. They are reminders that the universe, even in collapse, finds order. There are many types of pulsars. Some spin slowly, emitting pulses every second or two. Others, called millisecond pulsars, spin hundreds of times each second, their beams flashing faster than we can imagine. These rapid rotators are often found in binary systems, where the pulsar has stolen matter from a nearby companion star. As this matter falls onto the pulsar, it transfers energy, spinning it up like winding a spring. The result is a neutron star turned metronome, clicking through the void at incredible speed. Their light comes in many forms: radio waves, X-rays, gamma rays. Each pulsar has a signature, a pattern, and from that pattern we learn. We learn about the strength of its magnetic field, the speed of its rotation, the angle of its beams. We learn how old it is, how stable, how far it's traveled since its birth. Each pulse is a page in a quiet book, written not with ink but with timing. Pulsars are scattered across the galaxy. Some drift alone, relics of long-past supernovae. Others move in pairs, locked in gravitational dance with another star or even another pulsar. These binary systems are laboratories for physics, natural machines for testing the theories that explain gravity, motion, and time. When two pulsars orbit each other, their timing can be measured to such precision that even the tiny loss of energy through gravitational radiation, as predicted by Einstein, becomes visible. A heartbeat, slowing by mere nanoseconds over years, but detectable, measurable, undeniable. And through this slowness, through this precision, we see the shape of the universe. We see that time itself can warp and stretch, that gravity is not a force but a curve, that light follows not lines but arcs drawn by mass. All of this revealed by a flickering point in the sky, a pulse, a spin, a star that refused to vanish and instead chose rhythm. But not all pulsars last forever. Over millions of years, their rotation slows, their beams weaken. Eventually, their pulses fade beyond our ability to detect. They become silent, not gone, but too soft to hear. And yet their gravity remains. Their spin, though slower, continues. They drift farther from their birthplaces, becoming ancient wanderers, holding still within themselves the story of a death that became rhythm. From Earth, we point vast radio telescopes at the sky to catch their signals. Arrays of dishes, synced and listening, collect the whispers of stars that live beyond sight. We have found thousands. We catalog their timings. We build maps from their pulses. We name them by their rhythm. PSR B1919 plus 21. PSR J0437 4715. Numbers and letters that mark the beats of distant hearts. And with each one, we learn a little more about time. Not the kind we keep on clocks or calendars, but the kind that spans galaxies. The kind that curves with gravity. The kind that listens rather than speaks. There is something beautiful in their precision, something soothing. These stars do not waver. They do not panic. They turn again and again, holding steady as the universe swells around them. In a world full of change, pulsars are the keepers of constancy. They mark the seconds of eternity. So when we look up, we don't just see stars, we see timekeepers. We see the echoes of collapse turned into rhythm. We see what happens when the universe remembers, and we listen, carefully, because every flash is a promise that even in silence, even in darkness, there is still pattern, there is still pulse. There is still a star, spinning like a clock, somewhere far away, counting down the moments between fire and peace. Let us travel deeper into the dance of these spinning stars, and listen more closely to the rhythm they offer. For pulsars are not just timekeepers, they are storytellers. With every rotation, they reveal something about the past, something about the space they live in, something about the forces that shape the fabric of the cosmos. Their pulses carry weight, not only in frequency, but in memory. Each flash is a moment not lost to the void, but etched into the silence with unwavering repetition. In the quietest places of space, these spinning stars sing of the laws that hold all things together. Millisecond pulsars are among the most remarkable of these objects. They spin with such speed and consistency that we've begun using them to create a kind of cosmic GPS, a pulsar-based navigation system for deep space travel. Their regular pulses, sent from far across the galaxy, can be used to triangulate the position of spacecraft, just like satellites help us find our way on Earth. Imagine a future where we sail through space, guided not by compass or map, but by the heartbeat of stars. These stars, long dead in fire, now lead the way with rhythm alone. And their rhythm is not always singular. Some pulsars live in binary systems where they orbit closely with another star, sometimes a white dwarf, sometimes another neutron star. These systems are delicate balances of mass and motion. As the two bodies circle one another, they twist spacetime itself. The orbits shift, their timing changes, and through those changes, we can detect the ripples of gravitational waves, the faint tremble of the universe responding to the dance of stars. One famous pair, the Hull-Staler binary pulsar, allowed us to measure this loss of energy so precisely that we confirmed one of Einstein's predictions decades before we ever built instruments capable of detecting gravitational waves directly. In this way, pulsars are like lanterns hanging in invisible wind. We cannot always see the wind, but we see the sway of the light, and from that, we know what moves. The universe is constantly whispering, and pulsars are the pages on which it writes. Some pages flutter quickly, some slow with age, but all carry the curve of gravity's hand and the hum of time's passage. Sometimes these stars shift suddenly. A pulsar might experience a glitch, a sudden increase in its spin rate. It is as if the star hiccups, a tiny quake inside its crust causing a jolt in timing. Scientists believe these glitches come from the interaction between the superfluid core and the solid outer crust. The interior spins slightly faster than the outside, and over time, tension builds. Then suddenly the crust slips, the timing jumps, and we feel the tremble from across the stars. It is a reminder that even in precision, there is change. Even in order, there is movement. Other pulsars grow quiet. Their beams drift out of alignment, no longer sweeping across Earth. They become invisible to us, though they continue to spin in the dark. These are the missing pulses, the lighthouses turned away. But with new telescopes, new eyes in space, we sometimes rediscover them, dormant stars, still ticking, still alive. We catch their rhythm again and welcome them back to our cosmic map, as if hearing from an old friend who had only fallen briefly out of reach. In recent years, we have found pulsars that emit in both radio and gamma rays, double voices from the same star. These rare objects offer more than one kind of message, more than one tone in their whisper, and each tone tells us something different about their energy, their age, their magnetic field. These are stars with layers of meaning, each pulse an echo from different depths. And then there are the magnetars, pulsars with magnetic fields 1,000 times stronger than the average. These stars spin more slowly, but their magnetic force is enough to distort atoms, to create bursts of high-energy radiation, to twist the crust of the star with violent results. When a magnetar shifts, the universe listens. We have detected giant flares, brief, bright bursts of gamma rays from these stars, even from distant galaxies. A blink from a magnetar can shake satellites in orbit around Earth. This is power folded into rhythm, fury buried in silence. But even this fury passes, the magnetar quiets, the pulses return. The universe resumes its quiet ticking, because pulsars are not chaos. They are the calm that follows. They are the echo of structure that persists after the flame. Even the most dramatic among them speak with repetition. Even the wildest ones move in circles. Across the galaxy, pulsars mark the remnants of death and the persistence of memory. Their light is not the light of birth, but of continuation. They spin in patterns not because they must, but because nothing has broken them yet. And so, they keep time not for us, but with us. Their rhythm becomes our rhythm. Their steadiness becomes our understanding. We build observatories just to catch their songs. We sink entire networks of radio telescopes, arrays that stretch across continents, to listen with greater sensitivity, to resolve each pulse, each flicker, each change. These projects, like the European Pulsar Timing Array or Nanograv, are not just scientific instruments. They are ears. They are the way we lean in closer to hear the story the universe tells when it speaks very, very softly. And what does it say? That stars do not always vanish. That time can leave a trace. That rhythm can survive collapse. That order can emerge even from the heart of destruction. It says that the universe, vast and wild, still knows how to count, still knows how to turn, still holds its secrets in the hands of stars that refuse to stop spinning. So the next time you think of time, not as numbers or hours, but as something deeper, think of a pulsar. Think of a heart still beating in the dark. A heart that pulses not for attention, but for truth. A heart that carries the story of a star that burned, died, and chose to sing instead of fade. And now let us follow the pulses into the far distance, where time stretches and slows, where stars drift between silence and signal, where pulsars become more than spinning remnants, they become monuments. The story of these stars does not end in their discovery, nor even in their precision. It continues in how they shape the space around them, how they whisper across centuries, how their rhythm becomes a bridge between the collapse of matter and the endurance of meaning. A pulsar does not burn like a living star. It endures, a sculpture of time and gravity, turning in the dark with no need for light to prove it is still there. In the heart of galaxies, pulsars keep turning. They may not be visible to the naked eye, but their presence is written into the motion of nearby stars, into the waves of radiation that sweep outward, into the symmetry of spiral arms that stretch across the cosmos. These stars are anchors, not by mass alone, but by reliability, by the promise that something in the universe continues to count, even when everything else is changing. Sometimes we find them at the edge of globular clusters, ancient star systems that orbit the Milky Way like relics from its earliest days. These clusters are dense, crowded with stars, and inside them, pulsars are surprisingly common. The interactions between stars in these environments lead to collisions, mergers, close passes, all of which can rejuvenate old neutron stars, spinning them up into fresh millisecond pulsars. In this way, pulsars become a kind of second life, a reminder that even in aged parts of the universe, rhythm can be restored. These recycled pulsars tell us about the long arc of time, how the remnants of collapse can find new motion, how death is not a full stop, but a pause before repetition begins again. Their pulses are faster, tighter, often more stable. They spin with purpose, having absorbed the motion of another star. This inheritance is not loud, but it is lasting. It says, "Something passed here, something touched me, and I still move." Not all pulsars are quiet, though. Some emit giant pulses, sudden bursts of energy, thousands of times brighter than their usual emissions, lasting only milliseconds. We don't fully understand why they do this, but we know it is part of their nature. The structure of their magnetic fields, the twist of their beams, the arrangement of plasma around them, all of these may contribute. What matters is that, even in regularity, there is room for surprise. Even in clockwork, there is spark. There are places on Earth where the light of pulsars has been inscribed onto gold, literally. Aboard the Voyager spacecraft, now traveling beyond our solar system, a golden record carries etched diagrams showing the location of 14 pulsars. Their precise timing and positions are meant to serve as a galactic map, a way for any distant intelligence to locate where the record came from. In this way, pulsars have become the language of navigation, not just for humans, but for anyone, anywhere, who understands rhythm and space. What does it mean that we chose pulsars to represent our position in the galaxy? Perhaps because their pulses are simple and profound. No translation is needed, no context. A beam flashes, a beat repeats. Across the emptiness, the message is, "I am here, I am still spinning, I remember, we exist," and that is enough. In the far future, long after Earth has grown cold and the stars we know have shifted in their places, the pulses of some neutron stars will still continue. Slowly, steadily, their beams will reach out, even if there is no one left to receive them. This is not tragic. It is beautiful. It means that presence does not depend on attention. It means that some things in the universe are not undone by silence. And even those that do slow, those that eventually spin too slowly to beam their light toward us, remain present. They are still massive, still gravitationally active, still part of the galaxy's architecture. They may become undetectable, but they do not vanish. A dead pulsar is still a folded star, a still weight in space, a whisper without breath. The story of pulsars is not just a scientific tale. It is also poetic. It is about how something can be stripped of almost everything: light, fusion, fire, and yet still hold on to motion, still spin, still shine in a narrow, rotating way. It is about survival, not as an echo but as a pattern, a rhythm so persistent that it becomes its own form of life. And this rhythm teaches us. It teaches us that time is not only a measurement but a texture, that the future is built not only from what is loud but from what is steady. It teaches us that collapse is not always the end of the song. Sometimes it is the beat that follows, the pause that gives structure, the silence that creates space for rhythm to emerge. As we build larger arrays like the square kilometer array or the future deep synoptic array, we will find more of them. Pulsars hidden behind clouds of gas, pulsars in distant galaxies, perhaps even pulsars orbiting black holes. Each one will bring new rhythm, new truth, a new stitch in the fabric of what we know. And through it all, the universe will keep spinning. Stars will burn and die, galaxies will swirl and stretch, planets will rise and vanish. But somewhere always a star will be turning, a beam will be sweeping, a pulse will be marking time. So tonight, as you lie beneath the sky, know that above you, far, far above, a star is spinning. Not for spectacle, not for sound, but because it cannot help it. Because the laws of gravity and momentum and silence say, keep turning, keep pulsing, keep remembering the rhythm that made you. And as it does, its message travels outward past gas and dust, past comets and moons, past galaxies and void. A single beat again and again saying only, I am still here. I am still turning. I am still light even after the fire. There are places in the universe where time forgets its pace. Places where the seconds stretch like soft cloth pulled by unseen hands. These are not realms of noise or fire, but deep, silent pockets of gravity, where mass folds space and space bends time. They are not far in distance, but far in feeling, far in scale. Here, in these quiet wells, gravity holds not only stars and planets, but time itself. And as you drift closer to these dense centers, your minutes become longer, your hours more stretched, until time begins to lose its meaning entirely. This is not fantasy. This is the nature of gravity when it gathers tightly. This is time warped quietly. Einstein once imagined space and time as a single fabric, woven tightly together. Mass, he said, bends that fabric. A small object makes a shallow dent. A large object, like a star, presses deeper. And something as dense as a neutron star or black hole, that creates a canyon. And within that canyon, time flows more slowly. A clock placed near such an object ticks differently from one placed far away. The difference is not just theory, it has been measured. On satellites above Earth, in laboratories, and in the wild silence of deep space, we see it again and again. Gravity stretches time. Imagine standing at the surface of a neutron star. The gravity there is immense, billions of times stronger than on Earth. Your body would be crushed in an instant, your atoms distorted by pressure. But suppose for a moment you could survive. If you looked up toward open space, you would see time moving faster. The stars above you would age more quickly. Their light would redshift, stretching into longer wavelengths. You would feel the heaviness of seconds, the weight of each passing moment. And if someone were watching you from afar, they would see you move more slowly. Not because you are tired, but because gravity has pressed against time itself. This phenomenon is called gravitational time dilation. It means that time is not fixed, it bends in the presence of mass. The stronger the gravity, the slower the time. And so, in the presence of great density, the universe creates gentle warps in its own rhythm. These warps are not violent. They do not shake or crack. They are subtle, like the hush of a cathedral, like the breath between heartbeats. Time does not scream when it bends. It whispers. The deepest of these whispers occur near black holes, the ultimate wells of gravity. There, the warping becomes so extreme that, at the edge of the event horizon, time nearly halts. To someone falling inward, the fall feels normal. But to an outside observer, that fall stretches toward eternity. Light escaping from the edge slows and reddens until it vanishes. And the person falling, to the distant eye, they freeze in place, caught forever at the boundary of time. But black holes are not the only places where gravity warps the clock. Even here on Earth, at sea level, time moves slightly more slowly than on a mountaintop. The difference is tiny, measured in billionths of a second, but it's real, and it matters. GPS satellites orbit high above us, in weaker gravity. Their clocks tick slightly faster than clocks on the ground. Without correcting for this, our navigation systems would drift. A simple drive through a city would become a map of errors. Even in our everyday lives, we rely on our understanding of how gravity bends time. In space, the effect becomes more profound. Near neutron stars, where gravity is fierce but not absolute, the time dilation is strong enough to shift the very physics around it. Light emitted near the surface leaves at lower energy. Atomic processes slow. Radiation curves. These changes, recorded in distant observatories, help us trace the mass and shape of the neutron star. We don't need to land on it. Its pull on time itself is enough to describe it. Time dilation is also a form of memory, a record of how close a thing lives to gravity's grip. Two twins could be born together, and if one lives on a high mountain while the other stays at sea level, the mountain twin would age faster. By a fraction of a second, yes, but enough to be real. Now stretch that difference across stars, across millennia, and the effect becomes a chasm. Gravity doesn't just pull, it changes the pace of life itself. In the presence of gravity, time becomes uneven, like a stream flowing faster in the middle than at the edges. It never stops flowing, it is not broken, but its speed is no longer constant. This unevenness creates possibilities. It means that journeys through space are also journeys through time. It means that the structure of the cosmos is not just spatial, but temporal, built not only of distances, but of delays. A light beam curving past a massive object arrives a moment later than one passing through empty space. A signal from a pulsar near a black hole is stretched and softened. Gravity changes not what happens, but when. There is a kind of beauty in this. The idea that time, which we often think of as rigid, can bend gently under the pressure of presence. That the ticking of the universe adjusts itself to the weight of the world. That every star, every planet, every person carries within them a slightly different tempo, shaped by where they are, how fast they move, how close they sit to gravity's heart. In neutron stars, we see this clearly. Their immense density warps the space around them into tight spirals. Time slows in their shadow. Light curves tightly. Even their pulses, those steady beams of radio waves, arrive at Earth distorted by the gravitational landscape they cross. We must correct for this warping to hear their rhythm clearly. And when we do, the pulses align again, as if the star is reaching through time to speak to us in its true voice. Time warps not with noise, but with elegance. The equations that describe it are clean, graceful, not cluttered, but soft. They describe a clock that ticks slower, not because it is faulty, but because it is deep inside a well. A well made not of stone, but of presence. A shape in the fabric of everything. Even human hearts seem to understand this, instinctively. We say we feel time stretch when we are waiting, or stop when we are in awe. We speak of heavy moments, light days, dense hours. Maybe it is not metaphor after all. Maybe our words echo the truth of the universe, that time and gravity are forever intertwined, and that to live under the pull of Earth is to experience a slightly different rhythm than to drift far above it. And in that rhythm, in that quiet difference, is wonder. Because the next time you look up at a star, remember, you are not seeing it as it is, but as it was. The light has traveled. It has been slowed by gravity, stretched by distance, shifted by motion. What you see is a version, bent by space, delayed by time. And what you feel, the awe, the stillness, is your own clock syncing for a moment with something older, larger, more curved. Time does not resist this bending. It allows it. It yields. Like silk draping over stone, it flows into the shape gravity offers. And in that flow, in that yielding, the universe finds its quietest balance. Let's fall gently into the curves and folds of this deeper understanding, where time ceases to be a constant beat and becomes something elastic, something alive. In the universe, time is not a drum keeping strict rhythm. It is a tide, bending and slowing, curling around mass the way water moves around rock. The more massive the object, the more time warps near it. This is not imagination. It is the geometry of the cosmos, the way space flexes under weight, the way gravity sculpts not only the path of light but the passage of time itself. To understand this is to realize that clocks, even the most precise ones, do not tick the same everywhere. Near massive objects, neutron stars, black holes, even dense planets, the clock slows. Not in error, not in weakness, but by design. This is not something visible to the eye, but it is measurable in the very breath of the universe. Astronauts orbiting Earth experience it. Their clocks tick slightly faster than ours due to the weaker gravity above. If they remained in orbit for many years, they would return slightly older than their twins on the ground. And yet, no one notices in daily life. The effect is tiny, but stretch it out over greater distances, near deeper gravity wells, and the time begins to diverge. What is a second for you might be slightly longer for me. What is a year on Earth could be a different span altogether near a neutron star. And in this difference lies a gentle poetry, for it means that the universe is not flat in experience. It is textured, lived differently depending on where you are. The clock becomes a local thing shaped by the invisible curvature of space. A photon moving past a galaxy will stretch its frequency redshifted. The light slows as it climbs out of gravity's arms. This is not resistance. It is the way light respects space's shape, the way it chooses the longer path, the gentler descent. And so we see the sky not as it is, but as it was, with each beam of light delayed, curved, stretched by its journey. Now imagine two stars in a tight orbit, a neutron star and a white dwarf. Their dance is shaped not only by gravity but by time itself. The neutron star, spinning and pulsing, marks the seconds with regular flashes. The white dwarf circles it in tight precision, but the closer they move, the more time warps for each. And the radio pulses we detect from Earth, pulses as regular as a heartbeat, begin to shift. We must correct for gravitational delay, for relativistic drift. And when we do, we find the story hiding in the time. A ripple in spacetime, a loss of orbital energy, a slow drift that confirms what Einstein described a century ago. This ripple, a gravitational wave, moves outward at light speed, carrying with it the imprint of time under strain. These waves are faint, subtle, but real. They were detected directly for the first time only recently, but their effects had been seen before in the changing timings of pulsars, in the shifting orbits of stellar pairs. The universe was already whispering. We only had to listen in the right way. And when we listen closely, we find that time behaves differently in every corner. Near Sagittarius A, the supermassive black hole at the center of our galaxy, time slows dramatically. Stars whip around it at enormous speed, their orbits bent into ellipses by gravity. The closer they pass, the more their light is delayed. Astronomers measure these delays to map the mass of the black hole, not by touching it, but by watching how it shapes the pace of time. The stars become second hands on a galactic clock, turning more slowly near gravity's throne. In our own solar system, this bending of time is more modest but still important. The Viking landers on Mars, the Voyager probes, the rovers and satellites all account for relativistic effects. Without these corrections, signals would arrive late, locations would drift, navigation would falter. Even communication between Earth and the International Space Station must include a tiny correction for time dilation. These small adjustments are reminders that time is not universal. It is local. It listens to gravity. On the surface of a neutron star, this warping becomes a kind of identity. Its mass presses space inward so intensely that time slows measurably. A photon leaving its surface climbs out of a steep gravitational well, losing energy, shifting redward. To observers far away, the neutron star appears cooler, dimmer, not because it lacks heat, but because its light must work harder to escape. Even its heartbeat, the spin, the pulse, must be interpreted through the lens of warped time. The timing we receive is not the same as the timing it emits. But when we adjust for the curve, the heartbeat returns precise and calm, like a metronome hidden behind a lens. This interplay between light and time is a language of the cosmos. It allows us to read the weight of invisible things. We see a star orbit faster than expected and infer a black hole. We observe light bending around a cluster of galaxies and infer the presence of dark matter. These are not guesses. They are translations. Time has been bent, and we have learned how to measure the bend. In the silence of deep space, even time can ripple, not just slow or stretch, but tremble. Two neutron stars colliding send out a shockwave, a gravitational surge that reaches Earth and slightly compresses space itself. The arms of detectors like LIGO shift by less than the width of a proton. And in that shift we find proof time and space are not passive. They move. They breathe. They carry the memory of motion. And so the universe does not just unfold in space. It unfolds in time, warped, stretched, slowed, and curved by mass and movement. We walk through this time without noticing, but it shapes us. It touches our electronics, our satellites, our physics. It wraps around our bodies softly, altering our pace just slightly depending on how far we stand from the planet's core. This is the quiet truth of gravity. It is not only about falling, it is about packing. It is about rhythm. It holds us not just in place but in time. And in that hold, it shapes who we are, how we measure, how we remember. So next time you look at a clock, whether on your wrist or in the sky, remember, it is not absolute. It is part of a larger web, a curved surface, a stretched breath. And every moment you live is touched by where you stand, by how fast you move, by how near you are to mass. Time, like light, listens. It bends, it yields. And in that yielding, the universe tells its softest truths. And now we come to the quietest part of the journey, the space between seconds, where time, gravity, and light hold one another in a soft, unbreakable balance. We've followed the curvature of spacetime around stars and walked slowly through the heavy breath of neutron stars, where time falls inward just as surely as light. But what remains in that stillness? What truths are found when the ticking of a clock becomes so slow that it almost vanishes into silence? In these places, the deep darks, the gravity wells, the folds of the cosmos, we find not just science but serenity. Because time that bends also teaches. Time that slows reminds us that everything that moves can also rest. Everything that burns can one day drift. Consider the life of a photon. Born from the core of a star, it bursts outward, pushing through the layers of fusion and heat, then flies through space untouched, unslowed unless it crosses paths with gravity. Then its journey curves, it stretches, its frequency softens. In some parts of the sky, this redshift becomes a map, a measure of how far the light has traveled and how deeply it passed through curved spacetime. We learn not only where the photon came from, but how it was touched by the gravity of galaxies along the way. The light that reaches our eyes is not just light. It is time, folded and layered, shaped by everything it passed. And it is not only photons that carry time's imprint. In the orbits of stars, the structure of rings, the rhythm of radiation, we find the fingerprint of warping. The dance of twin neutron stars tells us how their mutual gravity curves not just the paths they walk, but the moments between each step. When two such stars finally spiral inward and merge, their union shakes the universe. The gravitational waves ripple outward, carrying not just information about the event, but about the space they traveled through. Every wrinkle in spacetime is a memory. We've begun listening to these wrinkles carefully, patiently. We've tuned our instruments to catch the smallest tremors, the faintest changes in length, the most delicate pauses in time. When a gravitational wave passes through Earth, it stretches the space between atoms by a fraction so small it's hard to imagine. Yet it is real, it is measurable, and it reminds us that the universe does not shout. It speaks in pauses, in pulses, in slow, deliberate warps of time itself. Even here on Earth, time is not flat. Stand on the beach and your seconds pass more slowly than if you climbed a mountain. Your position in gravity's gentle cradle changes the pace of your heart without you knowing it. These differences are tiny, but they matter. We account for them in our science. We factor them into our satellites, our clocks, our maps. And perhaps most importantly, we begin to understand that we are not separate from the rest of the universe. We are inside it, folded into its shape, bent slightly, ever so slightly, by the same quiet rules. In stories, we often dream of time travel, of stepping into the past or leaping forward into distant futures. But time travel is not only fiction, it happens every day. In space stations, astronauts age more slowly. In satellites, clocks tick differently. In gravitational wells, time itself stretches out. We are already moving through time unevenly. What changes is not whether we travel but how we notice it. And when we notice it, we gain something rare, perspective. We begin to see time not as a straight road, but as a landscape, with valleys and ridges, soft curves and sharp drops, a place where every moment is influenced by the shape of the world around it. A moment near a black hole is not the same as a moment on Earth. A day in deep space, drifting beyond gravity's tug, stretches longer than we know. And yet, all of it is still one universe. All of it still speaks the same language, just at different speeds. The elegance of this truth is gentle. It does not demand action. It does not insist on urgency. It simply offers a new way of seeing, one in which presence matters, where you are shapes how you experience time, and how you move or do not move shifts the way time meets you. A photon falling into a black hole will never return. To us, it slows, dims, fades. At the event horizon, time appears to stop, but for the photon, nothing changes. It moves as it always has, unaware that its journey has become infinite to our eyes. This dual truth that time can move and halt, stretch and remain constant, depending on the view, is part of the universe's deepest symmetry. In the far future, when galaxies have drifted beyond sight, when stars have cooled and space has grown quiet, gravity will still hold. Time will still bend. The warps will remain even if no one is left to feel them, because spacetime, once shaped, does not forget. A black hole that formed from a collapsed star a billion years ago still curves the space around it, still bends time, still tells a story without words or light, just with its presence. And we who are here now, who stand on a small planet orbiting a medium star, are shaped by those same laws. The time we live, the way we age, the path our thoughts take through each second, all are shaped gently by gravity, by the Earth's pull, by the moon's tug, by the sun's hold. And so every moment is not just a second past, it is a second shaped. To live in the universe is to live in curved time, to exist not in uniformity but in softness, in a rhythm that breathes, expands, and yields. And when we slow down, when we listen closely, we can feel it. The drag of time in deep space, the stretching of a second near a star, the quiet folding of the cosmos around something heavy and still. This is what it means to move through the deepest dark, not to be afraid of it but to understand it, to feel how gravity and time and silence are not enemies but companions, not barriers but invitations, and that in the slowest, quietest corners of the universe, time becomes more than a measure. It becomes a place where we can rest, a place where we can listen, a place where the pause becomes the poem. So close your eyes now. Let the silence surround you. Let the seconds slow. Somewhere far away, a neutron star spins. A black hole curves the light, and in that curve, time stretches like breath, soft, steady, and infinite. In the hushed heart of collapsed stars, where pressure rises beyond imagination and atoms can no longer hold their shape, matter becomes something new. It is not soft, not molten, not like anything we have seen or touched. It becomes dense beyond dense, pressed into a form so tight that a teaspoon would weigh a mountain. This is matter at its final limit, not broken but changed, not gone but compressed into a kind of stillness that defies ordinary understanding. These are the bones of the cosmos, the deepest, most ancient structures that remain after a star has burned, exploded, and folded into silence. Matter has many forms. It can be gas, liquid, solid states we know well. But under pressure it changes. Ice becomes liquid. Liquid becomes vapor. Metals stretch and bend, fracture and reform. But what happens when the pressure is so great that even atoms collapse? Inside neutron stars, this question is answered quietly, with gravity and silence. The atoms, once arranged in neat patterns, with electrons orbiting nuclei, are squeezed until there is no space left for orbit. Electrons are pressed into protons, forming neutrons. And then, packed together, those neutrons become the building blocks of something new. What results is not chaos. It is not dust or ash. It is a lattice, strong, rigid, enduring. At the surface of a neutron star, this lattice may be only meters thick, but it is the hardest material in the universe. Stronger than steel, stronger than diamond, it forms a crust of neutron-rich nuclei and electrons, held together by nuclear forces. Beneath it lies a fluid sea of neutrons flowing without resistance, a superfluid ocean that circles the core like a memory turned liquid. And deeper still, perhaps, a core of strange matter, quarks freed from their boundaries, swimming in a soup of color and charge. We do not know exactly what lies at the center. Our theories offer many visions: a crystalline lattice of neutrons, a core of hyperons, or even something stranger, a quark-gluon plasma, the very same state that existed moments after the Big Bang. But no matter the detail, all theories agree: this is matter pushed to its end. The final form before collapse gives way to the unknowable pull of a black hole. The bones of the cosmos are not made of stone or steel, but of density, of symmetry, of particles clinging together in their last possible arrangement. The strength of this matter is astounding. Scientists have simulated neutron star crusts and found they can withstand pressure millions of times stronger than anything on Earth. A mountain just 1 centimeter high on a neutron star would hold as much mass as Everest. And yet that crust can shift. Starquakes, sudden cracks in the rigid surface, can jolt the star's rotation, releasing bursts of energy that travel across galaxies. These quakes are not signs of weakness, but of tension. The bones flex, they adjust, even under such weight they move. This crust is layered like bark on a tree, like shell over heart. At the outer edges, where density is lowest, exotic atoms may still form, heavy nuclei surrounded by clouds of electrons. Deeper down, the electrons are forced into tighter spaces, moving faster and faster until they reach relativistic speeds. Eventually, the distinction between individual atoms fades. What remains is nuclear pasta, a nickname for the tangled shapes matter takes under extreme compression. These shapes, spaghetti-like strands, lasagna-like sheets, are the result of a battle between nuclear attraction and Coulomb repulsion. Nature, pushed into a corner, gets creative. Beneath the pasta, the matter becomes even more uniform. A sea of neutrons, perhaps with a scattering of protons and electrons, flows in a superfluid state. This means it has no viscosity, no internal friction, and can spin forever once set in motion. In this layer, the superfluid is threaded with quantum vortices, tiny whirlpools that store the star's angular momentum. These vortices can suddenly shift, causing glitches in the star's rotation. The bones of the cosmos, it seems, can twitch. As we move inward into the core, theory grows thin. Some suggest that the pressure is so great that neutrons themselves dissolve into quarks, the fundamental particles that form all matter. If so, the core becomes a new kind of star within a star, a quark core, perhaps even a strange quark matter core, more stable than anything else in the universe. If this is true, then neutron stars are not just remnants. They are windows into the earliest states of the cosmos, holding the same matter that filled the universe microseconds after it began. The pressure at the center is immense, over 100 trillion times the pressure found in Earth's core. At these levels, forces balance in perfect opposition. Gravity pulls inward, nuclear repulsion pushes outward, and for a time, a very long time, equilibrium is found. The neutron star does not collapse. It does not explode. It simply persists. A sphere of stillness, a monument to what matter becomes when all other options are gone. Even in this silence, heat remains. Newly born neutron stars are hot, temperatures reach into the billions of degrees, but because of their small surface area, they cool quickly. Within a few years, their temperatures drop to 1,000,000 degrees. Within 1,000,000 years, they cool even further, becoming cold and dark, invisible except to the instruments that can catch their fatting X-rays or detect their tiny pulses. Yet even cold, they do not soften. Their structure holds. The bones remain. From Earth, we cannot touch this matter. We cannot recreate it in labs, but through telescopes and theory, we glimpse its nature. We study the signals that arrive from pulsars, the X-ray bursts from neutron star mergers, the gravitational waves from distant collisions. Each one carries a trace of the matter within, a fingerprint of the bones themselves. By measuring how these stars deform under stress, how they wobble as they spin, how they ring after a collision, we map the stiffness, the strength, the hidden architecture. These structures are not just interesting. They are foundational. They show us the limits of matter. They reveal the invisible walls of physical law, the line beyond which atoms can no longer be atoms. In neutron stars, we meet matter at its most obedient, at its most extreme. The particles follow rules we've barely begun to understand. The symmetries of quantum chromodynamics, the theory of quarks and gluons, play out in full expression. Gravity and pressure wrestle and settle. And in the center, something new is born, stillness that holds weight, silence that holds form. These are the bones of the cosmos, not shaped by erosion or sculpted by time, but by compression, by gravity's quiet insistence. They are not ancient because they are old. They are ancient because they come from the first principles, the core behaviors of nature itself. They do not decay. They do not shift easily. They remain long after light has gone. So when we gaze into the night and think of stars as soft, glowing things, let us also remember what lies beneath. Let us remember that inside every collapsed sun is a truth so dense it no longer needs fire. A truth made not of light but of structure, not of sound but of presence. And in that presence the universe holds its shape. Now drift with me deeper into this dense silence, this realm where matter no longer floats or flows but becomes something nearly absolute. In this quiet interior of a neutron star, the boundary between particle and structure softens. Nothing here is ordinary. Even time slows slightly in respect. The crust, with its strange nuclear patterns, gives way to the inner layers where neutrons become the dominant form, a sea of single, neutral particles, densely packed, gently rippling with quantum precision. There is no space here for anything light or wide. All is tight, all is compressed. And yet within this density, a delicate kind of order emerges, one we are only just beginning to understand. These inner layers may behave like a superfluid, a ghostly state where friction disappears and motion persists forever without loss. Superfluids are not new to science. We've seen them in helium cooled near absolute zero. But here, the conditions are reversed. The temperature is high, but the pressure is far greater. The result is a neutron sea that glides perfectly, a substance more like thought than fluid, its ripples storing the star's spin, its flows marking the rhythm of ages. Embedded within it are quantum vortices, tiny whirlpools around which the superfluid swirls. These vortices act like pins in the fabric of rotation. When they shift suddenly, the star jolts, spinning faster in a heartbeat. This is known as a glitch, a quiet reminder that even the densest things can twitch. Above this superfluid heart lies the so-called nuclear pasta, where matter folds into patterns that resemble our world in eerie ways. Scientists have named these shapes not out of whimsy, but because they mirror structures we know: spaghetti, lasagna, gnocchi. Under the crushing gravity of a neutron star, protons and neutrons are forced into forms that balance competing forces: nuclear attraction, which tries to bind them tightly, and Coulomb repulsion, which tries to push them apart. The resulting structures are long filaments, sheets, and blobs, repeating like crystalline lacework in the dark. These patterns may control how heat moves through the star, how magnetic fields shift, and how the surface crust interacts with the layers below. Nature, even when compressed into extremes, does not abandon beauty. Farther inward, the boundaries between neutrons and protons begin to blur. Some theories suggest that in the deepest depths, matter becomes a quark soup, a fluid of the building blocks that form neutrons and protons themselves. Quarks, usually confined inside particles, may roam freely in this core. This would mean that the heart of a neutron star is actually not made of neutrons at all, but of their constituents: up quarks, down quarks, perhaps even strange quarks. This phase of matter is exotic, known as strange quark matter, and it might be more stable than anything else in the universe. If so, a neutron star with a quark core is not just a dead star. It's a seed, a kind of prototype for a new state of matter, one that could, in theory, transform other matter it touches. We have never seen strange matter directly, but the universe whispers of its possibility. The way neutron stars merge and radiate, the way their cores resist collapse, the patterns of their gravitational waves, all these offer hints. Observatories like NICER and LIGO, measuring the faint pulses and violent collisions of these stars, help us test these ideas. Each signal carries a trace of the star's interior stiffness, how easily it deforms, how strongly it snaps back. And in those traces, we search for evidence. Is there a fluid core? Is there a quark phase? Does matter truly reach this final form? The question is more than academic. If strange quark matter exists and is stable, then any contact with ordinary matter could transform it. A strange star, formed from the collapse of a neutron star, might slowly convert other stars it touches, spreading a new phase of matter through the galaxy. This sounds like fiction, but the equations allow it. The universe has already shown us that its limits are softer than we thought. From black holes to superfluids to dark matter, it continues to stretch our definitions. Still, these theories remain wrapped in silence. We cannot dive into a neutron star to see its core. We cannot bring a piece back, but we can listen. We can observe how these stars spin, how they pulse. Pulsars, rotating neutron stars with magnetic beams, send out flashes with astonishing regularity. Some spin hundreds of times per second, ticking like cosmic clocks. When we measure the intervals between these ticks, we find clues. Tiny shifts, tiny glitches, tell us how the star's inner structure stores and releases energy. These glitches are not flaws, they are breaths, adjustments. The sudden unpinning of vortices, the slip of a crust over a superfluid base, the ripple of pressure deep within the core. And just as bones in the body shift slightly with age or strain, so too do the bones of the cosmos stretch and relax in response to the forces they hold. These shifts send out tremors, not only in light, but in gravity. We've begun to detect these tremors, translating them into mass, pressure, and strength. The matter within a neutron star is also unimaginably cold, not in temperature but in entropy. That is, it is highly ordered. The randomness has been squeezed out. Unlike a flame or a gas which is disordered and chaotic, this compressed core is structured, stable, and nearly perfect. In some ways, it is the cleanest form of matter, stripped of impurities, stripped of space, stripped of anything that can bend. It is the universe reduced to its barest skeleton, held in place by forces that we've only begun to name. To study this skeleton is to touch the edge of knowledge. Every time we improve our instruments, we find that the neutron star does not flinch. It holds its silence, its strength. It deflects our questions with regular pulses, with tiny shifts, with patterns etched into the very shape of time. But still, we listen. We model. We calculate. And with each model, we build a clearer picture, not only of what a neutron star is, but of what matter itself can become. So when you look at the night sky, remember, not all stars shine. Some collapsed long ago, folding into dense remnants that no longer burn, no longer flare, and yet they remain. They spin. They pulse. They hold the story of what happens when all heat has fled, when all pressure has settled into balance. And that story is written in their bones, in the structure that endures long after the fire has gone. Matter, it seems, does not easily surrender. It resists compression until it cannot. And then when forced beyond the familiar, it rearranges. It finds a new state. It holds. Even in collapse, even in silence, it remains. And in that remaining, it becomes something else. Not just the bones of a dead star, but the pillars of cosmic truth, the shape that reminds us there are places still where matter reaches its limit and yet does not disappear. It becomes whole. Let us now sink into the final stillness, the deep, dark calm where all struggle has passed and only structure remains. Here, in the inner sanctum of the cosmos, matter rests at its limit, not broken, not ruined, but redefined. A neutron star does not glow with heat like its ancestor. It does not blaze or erupt. It persists quietly with a strength born not of motion, but of order. This is matter's final poem, not sung aloud, but held in silence. The bones of the cosmos, enduring in the absence of flame. And what does that mean for us who live in a world of wind and rain and softness? We build with matter that bends, melts, cracks, and heals. We walk on stone, rest on soil, cradle metals in our hands. But none of it comes close to the density found in a collapsed star. The neutron star is a whisper from the farthest edge of physical law, a monument to endurance. 1 teaspoon of its substance outweighs mountains. A single city block of its crust could withstand the blast of 1,000 nuclear suns. And yet, this unimaginable strength exists peacefully. It does not need to defend itself. It is simply there. Neutron stars do not often collide, but when they do, the cosmos listens. The merging of two such stars sends tremors across spacetime, gravitational waves that ripple outward, carrying the shape of the star's inner strength. The waves encode how the matter bends and rebounds, how stiff the crust is, how dense the core becomes before collapse. We have heard such a collision only once in detail, the famous event known as GW 170817. In that moment, telescopes and detectors across the world caught the light, the particles, the gravitational murmur of two bones shattering into one. And from that cosmic crash, heavy elements were born. Gold, platinum, uranium, these rare materials so prized on Earth are forged in such collisions. They are not made in stars like the sun. They are too heavy, too complex. Only the immense pressure of a neutron star collision can forge their nuclei, which means the ring on your finger, the wires in your electronics, the glitter in ancient rocks, all may have come from such a collision. From the bones of collapsed stars meeting in silence, fusing in darkness, and throwing their essence across the universe. We are, quite literally, wearing the remains of stellar bones. Over time, neutron stars cool. Their once fiery interiors radiate slowly into space. Without fusion to sustain them, they release their heat through conduction and neutrino emission, silent particles that drift through matter as though it were air. These neutrinos carry away energy, cooling the star to 1,000,000 degrees, then to hundreds of thousands, then eventually to near nothing. And still the structure holds. The crust stays firm. The core remains dense. The spin may slow, but the body does not fall apart. Even when cold and invisible, a neutron star keeps its shape. We think some of these stars may become black dwarfs in unimaginable timeframes, trillions of years from now, when all fusion has ended and the universe has cooled. But even then, their density will outlast planets. Their core, their lattice, their weight will remain. In this way, the bones of the cosmos are not just old. They are eternal, almost beyond decay. We have no evidence that a neutron star crumbles. We see no sign that its matter weakens. It may outlive galaxies. This invites reflection, because we too are made of atoms. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were formed in stars, but not like this. Not in the collapse, but in the life of stars, in the fusion, the burning. Neutron stars show us another path, a path of compression, not combustion, a way of becoming through stillness, not fire. And perhaps there is something to learn in that. Not all things that change must explode. Not all endings are loud. Some are simply a new kind of balance, a tighter one, a quieter one. And in that silence, a deeper truth is held. We often think of strength as something visible, steel and storms, flame and impact. But the bones of the cosmos suggest another kind. A strength so great it does not need to move. A resilience so complete it simply is. This strength comes not from size, but from density. Not from mass alone, but from what mass can become under pressure. The particles that make up a neutron star are the same that make up you and me. Quarks, neutrons, protons, all from the same family. But in the neutron star, they are arranged to endure, to hold against collapse, to balance gravity's pull with quantum resistance. The same laws that keep your body standing, electromagnetism, nuclear force, keep the star intact. And in that parallel is something comforting. We are not separate from these stars. We are made of the same cloth, stitched with the same thread. The only difference is arrangement, pressure, environment, fate. But even fate is not final, because the matter that makes a neutron star may someday drift again, ejected in a collision, pulled into a black hole, scattered into space, gathered into new forms. Some of that matter may fall into planets, some into dust clouds. Some may even find its way back into new stars. In time, it could return to fusion, to warmth. The bones may once again become breath. And so the cycle continues, not a circle, but a spiral. From burning stars to collapsed remnants, from glowing fusion to silent strength and back again. To witness this through science is not to lose the poetry, it is to gain it. Because what greater poetry exists than the knowledge that the hardest things are born of pressure, that stillness is not emptiness but density, that in the center of every collapse there may be structure, even beauty. So close your eyes now. Let this vision rest inside you. A star once burned, then fell. Its light left, but not its essence. And now, far beyond sight, it endures as bone, as weight, as the unshakable memory of matter's final form. In the soft dark between galaxies, it spins, it waits, it whispers. It does not shine, but it does not fade.